where I want to start today is let's see. Wednesday we looked at uh, we were doing the Boolean algebra and the logic stuff. We made a truth table, okay, that had uh, three inputs, no, four different inputs. So we had 16 different patterns that we could write down. So what I want to kind of do is talk about why I put them in the order that I did, and convince you that really what I was doing was counting from 0 to 15. Okay. So, in order to do that, let me just start with what does that number mean? Okay, yeah, it's the founding of Wabash College, but what is it? Like, how big is this number? Okay, now how do you know that it's 1,832? Yeah, because like you just know, right? Because we use a place value system where the position of the digit indicates its value. Okay, so if I write it, let me space it out here. Okay, so the 2 is in the ones place, which I'm going to write as 10 to the 0. Okay, and then each of the corresponding digits are in a place, and depending on which position they're in, that changes what value they are. Okay, so it's 1,000. How do you know it's not 100 or 10 or 1? Well, because it's in the thousands position, right? And you guys don't even have to think about this. I mean, maybe in elementary school or something you did, but now you don't have to think about it. You just look at it and you just know intuitively it's 1,832. Okay, and that's that. Okay, so uh, the place values here are all powers of 10. That's the counting system that we all use in the world, basically. And uh, Fortunately, everybody uses the same counting system because that would be really irritating if it was different in different countries. Uh, and yeah, but why 10 as the base, right? So why are there powers of 10? Yeah, it's easy to calculate, but there's nothing inherent about 10. Yeah, that's why. You have 10 fingers, basically. Okay. Uh, and You also have presumably 10 toes. There's no particular reason why 10, right? Like if we got in our time machine and went way, 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 way back, we could redefine things with any other base number that you wanted, and everybody would get along just fine, right? You'd get used to the new base, and if that's all you ever learned, then it would be just as natural to you as doing it in base 10. Okay, but in and I should say that base 10 has not been universally the base. Okay, uh, the Mayans used a base 20 system. Okay, there are vestiges even in English and French of counting in like base 12 or base 16. So, for example, in English, 1 through 10. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But what's next? Not 10, 1 or something like that. And then 12. Okay, but then the system switches how you say it at 13, 13, 14, 15, right? It switches at 12 from 12 to 13. Yeah.
So is that why clock is 12 and dozen is 12?
Uh okay. So the reason that the clock is 12, that's maybe a bit more complicated of an answer. Uh, the clock system that we use basically derives from the Romans, right? So they would have hours or watches where they would, somebody would stand guard. Uh, Now that begs the question: why did they do 12 in the first place? Uh, the reason they did 12, or maybe the reason that they're, say, 24 hours in the day, is that's more of an astronomical thing. Okay, and so this gets to a well, ancient Mesopotamian thing. How many degrees are in a circle? Why 360?
It's divisible by a lot of things.
That's why, right? It's divisible by a lot of things, right? So you can carve 360 up evenly into lots of different uh, things, right? Okay, so it's useful in that sense. And that's something that has stuck basically since, for 4,000 years or whatever. Uh, 12 happens to be one of the things that nicely divides into 360. It's 15, or sorry, no, 30, uh, and 24 and 15, right? So the sun basically moves across the ecliptic at 15 degrees an hour. Uh, and yeah, that's useful knowledge if you need to navigate or plant things or whatever, right? Um, okay, so even you guys use basically non-base 10 systems every day. The clock being the prime example of this. Okay, uh, even though we write it with base 10 symbols, right? So that's why 10, 11, and 12 have they don't there's not a special symbol for 12, right? It's 1 and 2, the two digits. Okay,
The clock is kind of base 60.
right. It's base 60 or base 360, and the base 60 bit, um, that even goes back to, again, the Mesopotamians. So they used it's sort of a hybrid of a base 10 and base 60 system. Uh, it was base 60, but they would write the numbers as if they were base 10. So, like, there wasn't, so if you wrote in base 60 truly, you would need 60 separate symbols for each number from 0 through 59. That's kind of ridiculous. Okay. So, the way that they would write them would be, like you would have, say, 12, 30, 45, okay? And you would understand that this was the 60 to the zero place, and the 60 to the first place, and the 60 to the second place, okay? Um, Although in their case, what they were usually doing was actually subdividing. So, so that uh, the more places to the right were actually fractional parts, and so it would be more like, let me say it like this. It'd be like 60 to the 0, 60 to the minus 1, 60 to the minus 2. And so this would be equal to 12 plus 30 60ths plus 45 60th squared, okay, or something like that, right? Um, Yeah, and so a lot of ancient trigonometry still uses this system, and in fact, we have the vestiges of it with degrees, minutes, and seconds. Right? How many degrees are there in a circle? 360. How many minutes are there in a degree? 60, same as how many minutes are there in an hour, and so on, right? So you guys, even though we primarily use base 10 for numbering things, that's not universally base 10. Uh, and even in currency, for example. So it wasn't until the early 1970s that the British currency system was decimalized. So it used to be that there were like 8 pence and a something and a 12 whatevers and a pound, or I forget the names for all the different subunits. Um, but uh, and it had been that way for basically 1,000 years or whatever, and then it wasn't until the like 1970s that they finally switched it to being a decimalized system where there are 100 pence in a pound and none of this weird funny division system. thing. So anyway, okay. So there's nothing inherently special about 10 other than, well, you have 10 fingers. So that would be sort of a natural choice for being able to count with. So why not other numbers? Like how about 2? Okay. And if I do that, then I only have 2 digits or 2 symbols to write down, 0 and 1. Okay. Now, the downside of this is that to write a number like 1832 will require a lot more space. Okay. The upside is there's only 2 digits. And in particular, this is brilliant because from a, like, if we think about a circuit standpoint and hence a computer standpoint, well, everything's either off or on. So makes sense to do that. Okay, so the way that the counting will work is exactly the same as we do in base 10. It's just base 2 instead. Okay, so if I were to write, uh, let's say, 2 to the 0, 2 to the first, 2 to the second, 2 to the third, okay, and this would be 1, 2, 4, 8 would be the values of the places. Okay, I could keep going, obviously, but let's just start here, right? So if I make up some random pattern like this, then how do we decode it? Well, again, we look at the place value, okay, and then we just add it up. So what do we have? Do we have an 8? Yes. Okay, so we got 8 plus 2 is 10 plus one more is 11. Okay, so the binary pattern here of 1011, okay, and I'll put down below the word 2 as a subscript just to indicate that it is in fact in binary as opposed to that this is 1011, not 1011. Okay, just so we know what we're talking about. This would be the same as, what did I say it was, 13? 11, yes. 5, Theresa. Right, 3. No, from Monty Python. You know, the holy hand grenade of Antioch. Yeah. Pulleth out thy holy pin. Okay, so this would be 11 in base 10. Okay, and again, I'll write the subscript there so that we're clear as to which system we're talking about. Yeah.
So did we just assign these 1011s?
Oh, I just made up 1011 completely arbitrarily, right? So I could write down any other pattern there, and then this would be how we would decode it. Okay. So yeah, like I said, I just picked 1011 completely at random. Okay. And if we think, though, this was actually one of those 16 patterns that I wrote down when we were doing our truth table stuff last time, right? Or maybe it was only 8 that we wrote down. Okay, but point being, right? Uh, when we did a big truth table last time, and we had a bunch of patterns to write down, and I wrote them down in a very particular order. What I was actually doing was counting from 0 to 15 in binary. Okay, so I just, and because it's sort of second nature to me now, having done computery stuff for so long, I just did it. Okay, so. Um, so if we write, so let's just write kind of all 16 patterns that we could if we used 4 bits. Okay, so a bit is short for binary digit. It's like a digit, except it only is a 0 or a 1. Okay, okay, so let's write all 16 of them down. If I use exactly 4 bits, okay, so I could have 0, which would be all zeros. I could have 1, which would be that. I can have 2, I can have 3, 4, 5, 6, 7, 8, oops, 9, 10, 11, which is the one that we just looked at, 12, 13, 14, 15. Okay, so there's all, let me zoom out a little bit so they're all on the screen together. There's all 16-bit patterns that we could write that use 4 bits. Okay, and there's a reason that I've chosen 4 bits as the number here for this instant. Okay, so you see how I'm kind of counting up? Yeah, does it sort of make sense-ish? It'll sink in, okay? Give it time. Okay, but the counting system is just like I was writing down the numbers from 0 through 999, right? 0, 1, 2, 3, and so on. Okay, it's just that I only have 2 digits here, 0 and 1, instead of 10 of them, 0 through 9. Okay, all right. So as you could imagine, numbers get really, really big if we start looking at stuff on a computer, right? This is only 4 bits, okay? And what kind of units do we use to measure data on modern computers? Yeah, bytes, but not just individual bytes. We're talking like giga or terabytes, right? So just ludicrously much data. Okay, so if I had a really, really big number, okay, I would not want to actually write it in binary because it'd be, this freaking long. Okay. So what we've come up with is an abbreviation scheme, or which actually means it's a separate or a different base of counting, and that's base 16. Okay, now you might think, why 16? Uh, the reason, or a reason, is because there are 16 patterns here. Okay, so what I can do is if I have a really, really, really long bit pattern, I can divide it into chunks of 4, and each chunk of 4, I'll do this abbreviation scheme. Okay, this abbreviation scheme is called hexadecimal, hex for 6, decimal for 10, 16. Okay, and the abbreviations, you guys are going to like this. I'll write them in blue. Okay, I'll start with those 10. Well, that's quite logical, right? Because when I was counting, like let's take, say, the 9, why do I know that this 9 is a logical abbreviation for this? Well, I have a 1 in which position? The 8th place, and a 1 in the 1's place. Well, that's 9, right? So what other symbol would I use there? Like the eggplant emoji? I don't know, right? Like, yeah. Okay. That's good observation, right? Because what's the problem that I'm about to run into? Right, I'm out of digits, right? So we have counting digits 0 through 9, so 10 of them. But I've got 16 things there. So I need symbols for the remaining 6, but I don't want to write them using multiple digits. I want a single symbol to represent 10. It's A. Okay, so for the last 6, we go into the alphabet. Okay, and so we have A, B, C, D, E, and F. Now, if our counting system that, the ancients had given us was base 16, we would probably have 16 separate symbols for these digits, and we wouldn't have to resort to using part of the alphabet. But that's not how they ended up counting, and so this is what we get. French, you could argue, is in some sense a base 16 system because, or think about Spanish. Like, what's the word for 15 in Spanish? Quince. What's the word for 16? Dieciséis. Okay. In French, the system switches from 16 to 17, right? So you have 17, not 16. There is no 16 en français. Okay. Which that's sort of interesting given that they're both Romance languages, how it ended up one way for the French and one. Counting in French, by the way, makes me want to just punch people. Okay. Because what's 87 in Spanish? Huh?
87, you said?
Yeah.
87.
Okay. So how did you do that?
80 is 80 and 77.
Okay. In French, it's 87, which is 4 20s and 7.
It's 90, it's 420, 10.
Yes, 4 20s and 10. Yes, 90, not 90, like a logical counting system. No, we have to count in, 20s. It's infuriating. Yeah. Okay, so this system in blue is called hexadecimal. Okay, so hexadecimal. And it's basically a base 16 system. So I could use this system on its own, or understanding that it's sort of an abbreviation for 4 bits at a time. Okay, so let's go back to, for example, our big number 1832 and write it in both of these new systems. Okay, all right, good for now. Okay, so let's take 1832. Okay, now if I'm going to actually start by writing this one in hex rather than binary, I could do it either way, but for reasons that you'll see in a moment, it'll be a little faster actually if I start with hex. Okay, so in hex, I have the 16 to the 0 place, the 16 to the first place, the 16 to the second place, and so on. Okay, so 16 to the 0 is 1. 16 to the first is 16. 16 squared is 256. Okay, and then it would go up from there. We won't need any more places for this particular number, but you can go as big as you want, basically. There's no limit to this. Okay. Okay, so what I need to know is how many 256s fit into 1832. Well, some number of them. Okay, uh, and how, if we didn't just know the answer or weren't like arithmetic geniuses, what would we do? Yeah, do the division. Okay, so how many times does 256 go into 1832? Yeah, 7 and some change. Okay, so it's 7 point whatever. All right, but 7. Okay, so how much did I just use? I just used 7 times 256. Okay, so if I subtract, that leaves me, so what I'm going to do is 1832 minus 7 times 256 leaves me with 40. Okay, so there's the remainder. Okay, good. All right, so continue. Huh? What now? How is that 40? Uh, well, I used my calculator. 1832 minus 7 times 256. Oh, yes. No. 7 times 256. Yeah. And why 7? Because it went in 7 times with some remainder. Okay. All right. So we've got 40 left, and we just continue this process. So how many 16 to the firsts fit into 40? 2. Okay. So now I'm going to do 40 minus 2 times 16 is 8. Okay. That's the leftover. And then in my last position, how many ones are there? Well, there's 8 of them. Okay. Yes. Okay. Right. So 7 to 8 uh, in hexadecimal, and I'll put a little subscript of hex to indicate this, is equal to 1832 in base 10. Okay. So just a different base, but otherwise everything works exactly the same. Okay. Now let's write it in binary. Okay. So for this, I'm going to take, it would take 12 bits to do it. Okay. How many hex digits did it take? 3. Each hex digit is a replacement or an abbreviation for 4 bits. Okay. So I just have to write down the 4-bit pattern for 7, for 2, and for 8. Okay. And let me actually scoot this over here so that I can expand this. Well, here, let me do it like this. So what is 8? It was 1000. What was 2? It was 0010. And what was 7? It was 0111. Okay, just take it 4 chunks of 4 at a time. And so that binary number that has 12 bits, okay, is the same or represents the same value as 728 in hex or 1832 in decimal. Okay, so just, yeah, 3 different counting systems. 1 you know, 2 that you just learned. Okay. Now, there is a way that we sometimes write this. So, which is we put 0B in the front. Okay, so I'll put that in a box. So 0 and then a little b to indicate that we're writing in binary. And then for the 728, sometimes we'll write 0x to indicate that we're writing in hex. Okay, and you'll see this pretty often in computer stuff. Okay, so we pretty much work like the guys that are in my other CS class, 241. Like we just think in hex. Like that's just it. Okay, um, and I'll kind of show you why. So, for example, let me just pull up one thing here. Let me go to the Mac. Let me switch screens real quick, okay? And I'll blow this up a little bit so it's easier to see. Uh, so what I'm looking at here is called a hex dump, okay, of a particular file, okay? This is a file, an executable file, so it's a program that we wrote. And what I was looking for in it is basically how some of the encoding is done. But everything I see here, it's all displayed in hex. So you want to do computer science seriously, you basically just have to think in hex, and you get used to it. It's not rocket science. Okay, but what I was in particular looking for is at the very beginning here, these 4 bytes tell me exactly what kind of file format this is in. It's in what's called ELF format, executable and linked file. So 7F, 45, 4C, 46, and so on. Okay, and each chunk of 2. Okay, so 2 hex digits. Well, how many bits does 1 hex digit stand for? 4. So 2 hex digits would stand for 8. Well, 8 is a very convenient number because that's how many bits we say are in a byte, B-Y-T-E, because we have to be cool, right? By the way, how many I just blew it. A nibble is 4 bits. And it's NYBBLE because, again, we got to be cool, right? So you can have a bit, you can have a nibble, or you can have a byte. Yeah? A byte is 8 bits. Yeah, exactly. And nibble is 4 bits. And the reason that talking about nibbles is useful is because each hex character represents exactly 1 nibble. So 2 of them represent a byte. Okay, right. So what I did this hex dump is I told the program hex dump, right, that I want it to display it to me in bytes, okay, and it formats it where there's a little bit of extra space here in the middle just to make it a little bit more readable, and then over here on the right it does ASCII decoding. We'll talk about ASCII later, and because some of these bits correspond actually to words, some of it's just data, okay? And so, but for example, like down here, you see there's this /lib/ld -linux arch64.so, right? That's actually text. That means something, okay? And basically it's specifying, well, what architecture was this program compiled for? It was compiled for 64-bit ARM, which is what's inside the Raspberry Pi, which is this little box there, that's a whole computer. It's not a very powerful one, but it's a whole computer. So anyway, okay. So hex and binary, and that's basically the system. So this isn't rocket science, okay? It just takes a little bit of thinking and doing some arithmetic, okay? And there's no limit to the size of the numbers that we could do here with this. There's just more places, right? In the same way that, is there any limit to the numbers that you can write down in base 10? No, you just have to keep going to the left with more places, okay? Although that does bring up sort of an interesting thing, which we'll talk about more. What I say, is there any limit to how many things you can write down or how big of a number you could write down? There's not really a mathematical limit, right? Okay, yeah, it might take you a million years to actually write that number down. Okay, but there's no mathematical limit to the size of number that you could conceive of. Okay, is there a practical limit? Probably. Okay, meaning that, well, if you write down the digits, and let's say it takes you a second to write down any individual digit, well, how many seconds are in a year? Okay, clearly nobody was a theater nerd in high school, because wasn't the 4 million? There's a song from a musical. Huh? Yeah, okay. But point being, so how many is it? Just Google it real quick. What is it? 5 million? Yeah. Well, or we could be useful here. Hey Siri, how many seconds are in a year?
1 year is 31,556,952 seconds.
All right, 31,556,952. Okay, so if you wrote down a digit per second, it would take you a year to write down a number that had 31 million digits in it. That's a big number, but mathematically, well, you can always do more, right? Yeah, got a lot of years. Okay, but in practical terms, with a computer, there is always some ultimate limit. Okay, uh, and the reason for that is, well, how much memory is in this computer? Well, depends, but like how much memory is in, say, your laptops or
16 gigs.
yeah, roughly 16 gigabytes, maybe 8, maybe 32. Okay, there's 16 gigabytes in my laptop, right? So there's only so big of a number that I can actually store. Okay, and if we what we have to do on the computing side is decide in advance how many digits we're going to use for to represent something. Okay, to represent numbers and what kind of encoding that we use to represent numbers. So, for example, how would I do 7.28? Uh,
16 to the minus 4.
well, okay, that would be a logical way to do it, but it's not the way we do it. Okay, for reasons that are actually quite logical, and we'll talk about encoding numbers versus in as integers, meaning whole numbers, versus encoding them in floating point, which is basically how you would deal with fractions, okay, or decimals. Okay? Uh, but when we do that, we have to decide in advance how many bits we're going to use for a different type of number system. Okay. Now, for most modern computers, the decision is usually 32 or 64, and they can do it either way. Back in the day, uh, you would count everything in 8-bit chunks. Okay. And so you could only do 8-bit arithmetic, and then you had to be kind of clever to do uh, more than that. Okay. So this has practical implications, which we'll talk about, called overflow, which is, okay, let's say that I use 8 bits. Okay, how many different bit patterns could I write down that are 8 bits? It's a pretty big number. 256. Now, how did we compute 256? It's 2 to the 8th. How many bits am I writing down? 8. Each bit can either be a 0 or a 1. And for the same reason, like what Wednesday didn't we talk about coin flipping? Right? It's the exact same thing. It's just we got 8 coins now instead of 3 or whatever. Okay. So 2 to the 8th happens to be 256. Okay. So what that would allow me to do is if I chose in advance that numbers shall be represented with exactly 8 bits, no more, no fewer, I could represent the numbers from 0 up through 255. Okay. And if I wanted to do bigger numbers, then I'd have to do some clever stuff. Okay. Or actually 0 through 255. I could have instead done minus 128 up through 127 and include some negatives in there. Okay. We'll talk about how we tell the difference between or how we do stuff with negatives versus positives later. Okay. But that's not a whole lot of numbers, right? So let's up the ante. Let's do 32 bits. Okay. How many different patterns would there be if we counted with 32 bits? It'd be whatever 2 to the 32 is, which happens to be like 4 point something billion. Okay. All right. Now let me split that in half because I'm going to say, all right, I'm going to count negatives and positives. So the biggest number that I could write down with 32 bits as an integer is 2 point something billion. Okay. That's a pretty big number, we would agree, but it's also not really all that big. Okay. That 2 point whatever billion, so this is, I love telling this. So how many of you guys watch videos on YouTube? Right? You should all be raising your hands because you should all be like, oh, Dr. McKinney, we love that you post the recordings of class on YouTube so that we can go back and look at stuff. And I'm sure you've liked and subscribed and hit the bell icon, right? How am I going to become a streaming multimillionaire now? Because you didn't like and subscribe and hit the bell, right? Okay, so how many of you guys have watched, say, music videos on YouTube? Okay, has anybody watched the Gangnam Style music video? Okay, so that video broke YouTube. Okay, because what happened is YouTube was using 32 bits to store the number of times that the video had been played. Okay, and they were storing it as a signed integer, meaning that it included negatives, because it might make sense to be able to talk about negative play counts. Like, let's say that they detect that you've got some bot that has been watching videos. Well, they should take those counts away, because that's just you trying to game the ad system. Okay, so yeah, so the video hit the 2 point whatever billion views. And then what happens when one more person watched it? It went back around to negative 2 point whatever billion. And that broke everything, right? That was a bad day, because whoever was programming this was like, oh, no video is ever going to get billions of hits. They just did 32 bits and called it a day. And then that video came out. Yeah.
Isn't that like the same thing of they talk about like the 2038 problem, where it's like an extension of like the 2000 problem?
Yeah. Yes, exactly. There's an overflow. Basically, is that it's going to happen eventually. With 2038, it's I forget the technical details, but yeah. So year 2000, what was sort of the problem? Well, we stored our date fields with 2 digits, right? 97, 74, whatever. And then what happens in the year 2000? It's going to be 00, which is less than, but even though it's actually after time-wise, right? So everybody, oh, I mean, you guys, none of you were alive for this, right? But everybody and their mother was just freaking out that, like, at the stroke of midnight, the entire world would just be plunged into darkness. And, like, there'd be riots in the streets, and people were, like, buying lots of canned food and ammunition and holing up in bunkers in Montana and stuff, because the world civilization was going to collapse in the year 2000. They also simultaneously forgot about the idea that there are time zones. So, like, we might have advanced warning that civilization was collapsing on the other side of the world before it collapsed here. Yeah, but everybody and their mother was freaking out. And they had to bring all these old programmers out of retirement to fix the systems so that they would use 4 digits for dates instead of 2. But yeah, it ended up being a big nothing burger, as it turns out. But hey, could have been worse. Right. So how we do integers, how we do floating point. We'll get to all of that, and then this idea of overflow. Okay. So what's weird about a computer or computer arithmetic is, and we'll talk about this more later. So if I ask you, give me a number so that when you add it to itself, you get 0. Okay, but you add the same number to itself, not a number and it's negative, right? So 0, right? Perfectly logical. Logical. Is there a second answer to that question? If you're working in, yes, an overflow or modular system, okay? So a good example would be the clock. Let's pretend that the 12 is replaced with 0. Okay, fine. Then 6, right? 6 plus 6 would be 0, but so is 0 plus 0, 0. Well, that's weird, right? Because that's not the way that you guys are used to doing arithmetic, because you're used to working in a system where there is no upper limit to the size of a number that you can talk about. Okay, but in a computer system where there is a fixed limit, we're actually working in a number system that's more like a circle than a giant line. Okay, and it's possible to come around that circle. Okay, anyway, so we'll talk about all these details later. But in the meantime, right, the key takeaways from today, let me go back to the iPad, is um, this system, right, of counting in chunks of 4 or in hexadecimal. Uh, 4 is a logical subunit to pick. It wasn't always what we picked. So, for example, back in the 70s, there were computers that used what was called octal, where you count in chunks of 3. And whoever decided that needs to be like burned at the stake for heresy. Yeah, choose a prime odd number. No, bad. So, anyway, all right. I will see you guys on Wednesday, and pay attention to Canvas for a forthcoming dump of assignments.